All right, so I want to give you a little bit of an update on Omni-Path. We've been doing a lot of work on Omni-Path over the last few years. A lot of the activity became public and started to be upstreamed in the last couple of years. So I'll give you a little bit of an overview of where some of the efforts stand and some of the results in the industry. Give you a little more insight into some of the innovations and some of the efforts that you've already seen and some of the ongoing work you're going to see in the near future as we upstream some more of the features and capabilities. So first, just kind of give you a very quick overview. Omni-Path is in fact a new fabric technology, and it is not InfiniBand. So while we leveraged a number of concepts and fully integrated with OpenFabrics, there's a lot of innovation, a lot of things that we did purposely different than InfiniBand in order to aim for better scalability and meet some of the more current requirements in the industry. We've been shipping Omni-Path in production all year now. And on the top 500 list as one litmus test, we had quite a few systems with Omni-Path in them, including a number 6 system at the Joint Center for Advanced HPC in Japan, and very good efficiency demonstrated on many of the systems. We also achieved a number 3 position on the newer list, the high performance conjugate gradient application. And so that actually placed us number 3rd, actually ranking with the fewest number of cores amongst all the top 7 on that list. So once again, demonstrating good efficiency and high performance in the industry. So fundamentally, the picture of the software architecture is very similar to other fabrics. We offer a host software stack that runs on all of the servers in the cluster. Above that, on a number of nodes, we'll run a management stack that provides centralized management functions to control and configure and operate all the nodes in the cluster. And then there is a fabric management GUI that can run on any workstation or laptop with a good screen and keyboard, and gives you an interactive access to the status and configuring elements in the fabric. From the software perspective, everything is tightly integrated into OpenFabrics, and we're leveraging all the elements of OpenFabrics that everyone here is familiar with. A lot of the recent work has been around the OpenFabrics interface, also known as libfabric. I believe some people are going to be talking a little bit more about that later this week. And so this has given a nice API that we can code to, and it absorbs us from some of the vendor specific details in protocols and in wire implementation, allowing for us to do innovation as a vendor without requiring applications to continually change what APIs they're using and how they're integrating with the stack. We continue to support performance scaled messaging API. That's part of OpenFabrics and was upstreamed about 7 or 8 years ago. And that's an API that was developed with a special focus around the needs of HPC and scalability and efficiency for high-end HPC applications. And then, of course, we also fully support the OpenFabrics verbs APIs and the ULPs that run on top of that, such as IP over IB and many others. But where Omni-Path is different is we've done a lot of innovations at every layer of the stack. And so a few of the innovations that are more visible to the software that we've done at the link layer include expanding the set of MTUs that are supported by the hardware. So we added 8K and 10K MTU support in the hardware. We've expanded a number of the resources, so we've doubled the number of service levels, and the architecture supports up to 31 virtual lanes. We've extended the address space, so the current shipping hardware supports 24-bit addresses, and we've got work in progress that I'll talk a little bit about to introduce the software model that is future-proofing us by giving us up to 32 bits of addressing. And then at the lower levels of the hardware, we've got some interesting innovations. We took a different approach to packet integrity protection than the InfiniBand folks, using a technique that's been used in supercomputers for a number of years based around link level retries. And so that gives us a much stronger mechanism for protecting the link and keeping latency low, even in the face of errors, and especially on links that have absolutely no errors, there's no penalty. We also had another feature, once again, around resiliency. As you heard in the keynote, resiliency is a big challenge at scale, and even getting a system to stay up and running for a week at exascale is going to be a challenge. And so we looked at all the elements in the hardware and wanted to make sure that we could keep things running and resilient even in the face of errors. And so one of the things we did is a feature called dynamic lane scaling, where you can have, for example, a 4x link up and running and moving traffic. If one of the lanes fails, we can shed it without losing any packets, without taking the link down, without losing connectivity, and continue to run traffic over that link as a 3x link or a 2x link or even a 1x link without resetting the link, without losing the connectivity. So this gives us very good resiliency in the face of those inevitable errors that are going to occur at huge scales. We've also done things to optimize the interaction of applications of various types on the cluster. So at scale, jitter is a very important problem and a very important challenge to solve, especially at exascale. And so one of the challenges you have is in most of these modern clusters, you're running at least storage and compute at the same time, perhaps multiple compute applications of various priorities and various degrees of latency sensitivity. And so we actually integrated into the hardware the design for a packet preemption feature that we call traffic flow optimization. And what this means is we can have a packet start that perhaps is a big storage packet, and then if shortly after it arrives at the queue, a small latency sensitive compute packet, we can preempt the big packet, insert the small packet in the middle of the traffic on the wire, and then resume the big packet without losing any data or losing any bandwidth on the wire. And so this allows us to carefully control the jitter that you'll see at large scale that becomes such an important factor for scalability of applications on very large node counts. Another thing that we did is a different approach to how we managed virtual lanes and avoided topology deadlock. So at exascale, there's a lot of need for advanced topologies that are distinct from the typical trees that you see in a more traditional deployment in the mid-tier of the 500. And so we added a technique that we refer to as a service channels that gives us a technique to do deadlock avoidance. And one of my colleagues will be talking a little bit about some of our routing algorithms later this week. But this technique lets us do it in a single service level. So we don't have to have multiple service levels in order to identify different virtual lanes that will be traversed during the fabric. We can do with this other technique. And so that's another element that we've innovated on that trickles into some of the routing algorithm and some of the other features that we're upstreaming. We also step back and look at the management from a much more scalable point of view. When InfiniBand was designed in 2000, there was a desire to make sure all the management could fit in a 256 byte packet. That was the low end of what was allowed in the spec, so they had to make sure everything could work. But that really constrained the efficiency of the SMA protocols because you can only have 64 bytes of real attribute in a 256 byte packet after you accounted for headers and directed routing and such. And so we expanded all the management packets to 2 kilobyte, and you'll see that this was upstreamed last year and is now part of the OpenFabrics core architecture. And this let us revisit all of the management protocols so that we could identify how to best lay out the attributes, how to take advantage of these larger packet formats to get more information, and of course accommodate new fields and new features that we had to be able to configure and monitor in the fabric. And so this applied to all the agents, and of course then the RMPP protocols that run on top of the administration can take advantage of this for greater efficiency as well. Another area of innovation that you've seen some activity in OpenFabrics for is around P-key-based security. In data center clouds, in HPC clouds, and in the industry in general, security is getting much more attention. And so we wanted to be sure that we could secure the management protocols so that a rogue node did not have an opportunity to try and take over the fabric and become a fabric manager and perhaps do various malicious things. So we took a very careful look at security and actually built a security model that secures the fabric without trusting any software or any firmware on the compute nodes, and allows us to secure the management packets throughout the fabric to make sure only the fabric manager can be issuing them. And we chose a technique based around P keys and introduced P keys as part of the SMA packets. We also have extended the number of counters and added capabilities and larger counters. So we re-architected a number of elements in the PMA protocols and created a well-defined performance administrator protocol above that for management tools to get access to data that the performance manager is gathering. And so later this week we have a presentation that will explain a little more in detail about the performance managing and monitoring architecture and some of the features that we've put in there. We've also been doing work and have upstreamed a number of things already around scaling the SA client side of things. So address resolution is really the heart of the SA clients, and that needs to scale as well. If you have hundreds of thousands of nodes all trying to either synchronize with a centralized repository of information or trying to query the SM at job launch or trying to establish a connection, that just doesn't scale. And so we've built into IBACM over the last few years a plug-in architecture that will allow a variety of strategies to support scalability. So at the more ad hoc clusters, the existing strategies that involve caches and more point-to-point oriented communications work very well. You get to 100,000 nodes and different strategies will be necessary, and this plug-in architecture will allow the strategies and the degree of pre-configuration that the sysadmin needs to do to vary based on the needs and size of the cluster. We also recognizing once again that at exascale there are going to be failures, there's going to be alpha particle hits, there's going to be components that fail out prematurely, and so at that scale you need better diagnostics. And so we've built a lot of features into the hardware, and these manifest themselves in additional information in the SMA and PMA to help us understand the nature of things. For example, when a link goes down, there's a link down reason in the SMA packets that we can now query, why did your link go down? Was it because of signal integrity? Was it because your neighbor rebooted? Was it some other reason? So we can better identify problems that need attention because they might represent a faulty component versus problems that are part of normal operations, like I rebooted the server next to the switch, right? And then a key element that we did is we wanted to make sure everything was very forward compatible, made sure that the investment that the industry has had in software and applications on OpenFabrics was fully available immediately day one on Omni-Path. So we made sure that the key things used by applications all continued to work on Omni-Path. So for example, we support all the IB style SA queries that are typical of application name services like multicast member record joins and path records and service records. We chose to open source everything. Literally every piece of software that we run that's Omni-Path specific, that's on a host, is upstreamed and open sourced. So we've open sourced obviously all the drivers, the providers, the libraries, all of the management software full featured with including our FM GUI, all of the OpenFabrics enhancements that we've done that I've mentioned so far and the ones that are ongoing. And we've also had a strategy of getting this into the distros because many of the mid-tier adopters want to get the entire solution in the distro and look at the distros for their support. So we've gotten to the point now that in Red Hat 7.3 and SLES 12 Service Pack 2, the entire Omni-Path stack is included in box in a supported status by the distro. So that will allow those customers that want a supported solution from the distro to have a full and complete solution. But we do have ongoing improvements and ongoing efforts that we're engaged in. And so the way we're approaching that is for anything that we're doing in the OFA areas, in the core of the stack, in APIs, we take a community collaboration approach where we collaborate with the community and kernel.org first, get agreement on the API changes, get the enhancements into the upstream, and then we have a variety of paths to getting that to the customer. So, one of the paths is what we refer to as a Delta distribution. One of the paths is what we refer to as a Delta distribution that I'll talk about a little bit in a moment. And that gives us a vehicle to get things to the customers before the distro has included them. And that way we can support customers, but we do it in a very surgical way in order to ensure that we're minimizing change to the distro. And that also gives us a way to get newer features out very quickly for the early adopters that are requesting new features, integrating with new applications, adding enhancements to existing features, or tuning performance on certain environments. We then include the open source, everything that we release in our, even in our Delta package, includes source RPMs for every component, as well as we open source everything on GitHub in the 01 org subsystem. We also have taken an approach of collaborating with the OpenFabrics Alliance in the libfabric efforts to continue to get APIs in place that allow us to provide vendor and hardware innovations with less changes to the APIs moving forward, so that we can have a scalable approach to the continual evolution of interconnects that are going to be necessary to meet the demanding requirements of the industry. So to explain a little bit about what we're doing with the OFA Delta, this is a representation of a single release of our Delta and how it might be affecting different distros. So Omni-Path came out after Red Hat 7.0 and 7.1 had existed, so our distribution for those needs to have a few features added to OpenFabrics, but we purposely don't replace all of OpenFabrics. We just add surgically the features that we needed, such as the 2 kilobyte MADs, to allow the Omni-Path software to run on that particular distro. As we get out here to Red Hat 7.2, that's the first distro that included all the Omni-Path enabling features that were required in the core of OpenFabrics. And so in that distro and later, we don't have any Omni-Path changes in the heart of the distro. And then over time, future distros continue to add feature from different vendors, including ourselves, into the common parts of OpenFabrics that will continue to have an increase in feature content with newer distros. And then for the Omni-Path specific things, such as our drivers and some of our fabric management and other components that are not common with other interconnects, we can have a little bit different strategy. So starting in 7.3, we had all of the features that we needed in the distro, and so that was fully functional, but after 7.3 was shipped, we still had some new features that we were developing. And so over time, once we hit this 7.3 plateau, the amount of things that we have in our Omni-Path specific bucket is going to be non-zero, but relatively small, and the distros will continue to grow as they pool from upstream and have the forward-looking features coming out in a timely manner. And so we feel that this strategy mixes the right balance between getting the new features and advanced tuning and capabilities to the early adopters that are demanding it ASAP, while still fully supporting the distros and ensuring that we're not forking the APIs or creating challenges for forward compatibility for customers as we move forward. So it's, we've gotten a lot of successes and a lot of things in, but there have been a number of challenges along the way, and we're continuing to work on a number of these challenges. First and foremost, one of the biggest challenges we found in integrating with OpenFabrics, as I think others have said, is that when we look at verbs and the OFA core, it's very InfiniBand oriented, and so it propagates in a number of ways. There are cases where we had to make design decisions in our hardware to be able to support the OpenFabrics APIs. We've got features that are unique to our cards, such as supporting 32 SLs, that right now we don't have a forward compatible way of advertising to a user space application that it's an Omni-Path card or that has that capability. So we're working, we've got various proposals and patches that are in flight there to work on ways to better identify capabilities to the user space APIs that may be unique to a particular model of hardware or a particular vendor's hardware. We've also found littered throughout the stack are a lot of IB-specific constants and enumerations that give us angst. So for example, rate is a IB-defined enumeration. We support a 3x link. That is, at the 25 gig sing link, that's a 75 gigabit link. There is no enumeration value for 75 gigabits. We had to use the 80 gigabit one as close enough. And so those are the kind of challenges that we've been running into. And so we're trying to work with the community on getting those things addressed, but these are things that we need to consider. And this is one of the areas where libfabric helps to abstract away some of those details from the application so that these kind of constants don't percolate their way into the hearts of applications. Another area that we've got a lot of active work going on now is getting the extended addressing in. The community and kernel.org has been reviewing and discussing for the last few months a set of patches around that. The general consensus in the kernel.org community has been that we should go through all of the kernel fabric APIs and increase the size of addresses in them so that internal to the kernel it can be a very clean approach. In user space, it's a little more challenging. We certainly don't want to break forward compatibility with existing apps and existing binaries. So the patch set is basically overloading fields in the global route portions of the path records in order to carry the extended lids. We've had some challenges and continue to have challenges, and this is another topic that came up at a previous OpenFabrics from another vendor, is getting some of the extended MTU features in. So there's certain applications in ULPs right now that assume 4K MTU is the largest allowed. In some cases we can use tricks like, hey, the values that we've chosen to represent 8K are the next logical power of 2. So extend the enum to the next logical value and it'll work. But in some applications this does create surprises, especially if they try to display or interpret the value. In many applications it works fine because they'll just pass it through. But this does cause us some headaches because a number of the verbs benchmarks won't accept values of 8K MTU. And so some of our performance can't be shown in the micro benchmarks even though it works in the real applications. And then we've also run into a few places where the management interfaces make assumptions that it's InfiniBand and use IB style MADs. One of the ones that was a little bit of a surprise that we had to deal with that's presently handled is SRP wanted to go find what devices might be offering SRP targets. So it wanted to go query the SA for all the port info records in order to figure out who had a device management agent. Our port info record does not look anything like InfiniBand's, so we had to fabricate a response that met the needs of what SRP wanted to do, and our security model says many of the fields in port info should not be available to general applications because that can be a vehicle to try to attack the fabric. So a number of the fields we have kind of filled in fixed values that are not representative of the hardware to meet the needs of SRP. But that's an example of a place where unfortunately InfiniBand has kind of propagated too deeply into some of the ULPs. And so as we try to introduce new fabrics and new innovations, we had to work through some of these things. Another interesting example is we did not limit the ability to send SMPs strictly to QPair 15, or excuse me, QPair 0, and so we can we can send them on any UD QPair even for the SMI interface. But right now that's a little more difficult to do through the OpenFabrics stack. Why would you want to do that? Well, on the SM side of configuring a large fabric, you may want to have multiple threads and multiple queues sending and receiving the packets and traps that it takes to initialize a fabric, while on the agent side having a single QPair is certainly adequate. So we do have quite a bit of ongoing work going on, and a lot of collaboration. There's a lot of fabric scalability work and things that we've been upstreaming. We also are trying to get discussions going around creating a standardized interface for doing snoop and packet injection into drivers. So In our labs, we take advantage of Wireshark. We've upstreamed a lot of Omni-Path packet decoders into the Wireshark project. You use features in our hardware in order to inject packets of arbitrary design into the fabric to verify error handling paths in various components. We even have fabric simulation capabilities where we can turn a host into a fabric simulator that then responds on the fabric as if it was another type of device or even an entire subcluster of a fabric. And so that lets us test the standard management tools and other elements against a simulation, so we can test things at scale without building out a 100,000 node cluster in our lab, which I'd love to do, but somehow our budgetary people don't really want to do that. And then we also do things with hardware emulation, where we can glue real fabrics into emulation models for future hardware that we're designing. And these packet injection mechanisms allow us to verify the interoperability and capabilities of that future hardware against current existing implementations. We're also, one of the challenges, once again, at scale is debugging things. And a lot of the strategy in OpenFabrics right now is to turn on logging. Well, that's good if you know the problem is going to occur, or, aka you figured out how to reproduce it, or if you're willing to deal with a lot of clutter in your logs for all this extra information that might help you debug a problem, and the clutter by itself might create other problems in terms of performance. And so, what we really need to work out in OpenFabrics is a technique to do historical tracing in a manner that won't impact performance and won't clutter the logs, but still allow the data to become available after the incident, so you can go back and figure out how you got into the erroneous state. And once again, help to diagnose whether this is an alpha particle type problem, a software bug, a hardware bug, or some other incident. And at scale, these problems are often difficult to reproduce, or nobody wants to dedicate a big cluster to trying to reproduce a bug. They want to take the first incident, gather the data, and then solve the problem based on what you can obtain out of the first incident. We've done some work in the SA area, but there's still work to be done. One of the interesting challenges in the current implementation of the interface is that when you issue a UMAD request in order to do an SA attribute, you have to specify a timeout for receiving the response to the entire attribute. And so most applications, not being sure what size fabric they're on, generally specify a rather large value, because there may be a large number of RMPP packets, and there may be contention and competition at the SA that slows down the response. So many of the applications are hard coding timeouts like a minute or two, and this is sometimes necessary at huge scale, but the downside is if somebody runs one of those queries and the FM is offline or the node is not on the fabric or something, the end user sits there for 2 minutes seeing no answer through the UMAD, when in reality you could have figured out that the first packet of the RMPP had timed out and told the application, hey, you're not going to get your response, and that could have been a much more timely timeout. So we're looking at that and how to improve that. And part of the heart of that is some of the work that we've already done, and we'll be talking about a little bit later this week, around getting really all of the applications to follow an architecture where the SA queries go through a common code path involving the IBACM plugins, the IBSA. And so by going through a common code path, then there's a single point of control where we can manage these timeouts. And so, for example, we could configure the timeouts in one place based on the scale of the cluster, and not have to go visit every application in every hard-coded place that somebody has put a timeout, but rather have a sysadmin controllable configuration in one place that would describe how to scale the timeouts or other behaviors based on the nature of the cluster. We're going to talk a little bit more this week about another thing that we're introducing and starting the upstreaming process on now, which is a virtual NIC driver, which is a Ethernet over fabric technique that we've implemented and our hardware is optimized around. And this gives us an approach involving some new Ethernet management agents that'll be in the host for configuring and controlling this virtual NIC. And it will also, we're working with the community on how to get the virtual NIC IP addresses as the mechanism in RDMA-CM for path resolution, so that you can choose that administration, whether to use IP over IB, which is glued into the heart of RDMA-CM and IBACM for helping with path record resolution, or if you're not running IP or IB and you're using VNIC, how to use those IP addresses to get the similar information. So, in summary, Omni-Path is out there. It's in production. We've got a lot of installed sites. The public list on the top 500 is a good indicator. But there's a lot of differences and a lot of innovation. And so we've introduced all these things through the OpenFabrics Alliance. Many of them have made it into the distros and upstream. But as we've seen from the needs of the industry, there's an ongoing effort and ongoing need to continue to innovate, because we're not at the end goal of an exascale system yet, and we're not at the end goals of other sections of the industry that are looking for other types of scalability and other sorts of advanced features. So we've got it there, but we're probably never done, because there's always going to be a next hurdle or next goal for the industry. And so we've got a model that open sources things, focuses on collaboration, but has a Delta way of getting things to customer quickly, especially for those early adopters and those leading edge systems. So we're continuing to work, and we appreciate all the help of the community. This has been a great community. We've really gotten a lot of capabilities into the hands of customers through the collaboration in the community, and we thank you for all your help.
Sorry, Todd, I'll throw you a low ball here. So it looks cool, right? I mean, I think people are excited, interested. But we sit at the OpenFabrics conference here, and so there's some advantages for interoperability, right? And so do you see anything, IBTA, anything, InfiniBand interoperability, how to leverage that so that there's more than going on just what Intel's doing inside, right? And leveraging off of, sort of this common software development effort that's outside, right? So, and I think it's, it's an issue for us.
Yeah, so there's a number of strategy and methods that we do have for interoperability. So, for example, a common technique in many of these clusters is that you'll have a storage subsystem, perhaps serving many clusters. And so, we've got Lustre forwarding engines are usually part of that, and so that can give us a vehicle to connect to existing storage clusters. The VNIC mechanisms, give us a way to interoperate well with existing, applications that are designed and dependent on features of Ethernet. So we're trying to find that careful balance of, pushing forward the exascale needs while interoperating with some of the key things that are required by our customers. But fundamentally, we didn't want to compromise on the features of the core fabric, because in order to get to exascale, it's going to take a no compromises approach.
So large MTU 8K, 10K has some application compatibility issue. I hope this will be addressed soon. After that, can the Omni-Path scale the MTU size up further? And how do you get to the decision of 8K, 10K instead of 16K, 32K, or even 64K? Is switch part of the consideration?
Yeah, so choosing the MTUs to support is an interesting mixture of trade-offs. The larger MTUs reduce overhead, but they do require more buffering in the switch. And compromises on the number of virtual lanes and other capabilities. We've got some pretty unique features I didn't go into around how we handle buffering and things in the switch, very reconfigurable, very dynamic abilities to adjust buffering while traffic is moving. But fundamentally, we looked at it as 8K as the next logical step, and that really got us the performance efficiencies that we wanted. And then 10K was chosen because the Ethernet industry, has standardized around, a little bit over 9,000 byte MTUs as jumbos, and we wanted to make sure that the virtual NIC capabilities would be able to support applications that had been designed for jumbo frames.
Okay, thank you.
Yep.
I'm a bit wondering about the 8K and the 10K MTUs. How are you planning to support this? The Linux kernel does not support the reliable allocations of anything above 4K. So if you do an 8K allocation for your single packet, you would have to virtually map that thing to be able to reliably process that. Since there could be a significant pushback from the core developers if you try to have an MTU size larger than 4K at this point.
Well, so MTU size is different than message size. The APIs and the memory locking schemes already support large messages, scatter gather of messages across various 4K pages that are often not contiguous in memory. And so, the MTU is relatively independent from the paging characteristics. It's more about being able to optimize the header processing that you're going to have in both hardware and other places as you scale up to the wire speeds.
Well, but this means that there's a lot of assumptions in the RDMA stack at this point that you can just allocate a single 4K page and that your package will fit in there. So you may have to have some work ahead of you to change that.
Well, that may be the case for the UD-oriented applications, but many of the applications we're focused on are more focused on reliable connected or OFI type interfaces that are dealing with more of a connection-oriented, large message type interface. So for example, big data applications will often have megabyte messages that they're trying to send.
Oh, okay. Thank you.
Or excuse me, machine learning applications. Yeah.
So we had the same issue, Christoph, with NFS, and so the problem was the deadlock in the VM system, and Hellwig, rejected actually some patches associated with that. So I think it's not a trivial issue, and it prevents us from moving forward right now in areas that we'd like to move forward to. So.